Designing and sizing a solar system is one of the most important skills for any installer. This ensures the system can handle the expected load without failing. Here's the step-by-step process. List the appliances. Write down every appliance you want to power, along with its wattage. Calculate total load. Multiply the wattage by the number of appliances and add everything together. Select an inverter. Choose one that can handle the total load plus 20 to 30% extra for safety. Size the batteries. Decide how many hours of backup you want, then calculate the required battery capacity in amp hours or kilowatt hour. Size the solar panels. Panels must be able to recharge the batteries daily, so we calculate how many watts of solar are needed to supply the required charge current. Let's walk through a simple example. Suppose we want to power 15 LED lights at 30 watts each, a 100-watt TV, and a 50-watt fan. That's 15 times 30 is equal to 450 watts for the lights, plus 100 watts for the TV, plus 50 watts for the fan, which gives us 600 watts total. To run this, we'd select a 1 kVA 800-watt inverter because appliances may have startup surges, and it is important to choose an inverter with continuous capacity comfortably above the 600 watt. To size the battery, we must move from instant power to daily energy, watt-hour, using usage hours. The battery capacity is calculated depending on the desired backup. For a practical approach, let's make some assumptions on usage hours. We assume that the lights are used 5 hours per day. That's 450 watts times 5 hours, which is equals to 2,250 watts-hours. The TV is used 6 hours per day. That's 100 watts times 6 hours, which equals 600 watts-hours. And the fan is used 7 hours daily. That's 50 watts times 7, which is equals to 350 watts-hours. Total daily energy is equals to 3,200 watts-hours. Now, converting to amps-hour at 12 volts, we have 3,200 watts-hours divided by 12, which equals 266.7 amps-hour. Hence, we will select a piece of 12-volt, 280 amps-hour gel battery for the battery bank. For additional hours, you can increase the battery bank. PV sizing array. By standard, it is recommended that the charge current of a lead-acid battery should be 10 to 15% the amp-hour of the battery bank. The battery bank capacity in this case study is 280 amp-hour, therefore, we will require 10% to 15% of 280 amp-hour, which is equals to 28 to 42 amp. For these specifications, let us consider 4 solar modules of the specs: 250 watts, open circuit voltage of 16.2 volts, maximum operating voltage of 12.8 volts, short circuit current of 9.4 amps, and maximum operating current of 8.3 amps. When the modules are connected in parallels, we will have a PV array giving an output of 33.2 amps, 12.8 volts and 1000 watts. To size the charge controller, we consider the input current into the battery bank, which is between 28 amps to 42 amps, and from our calculations, it is 33.2 amps, therefore we will select a 40 amp, 12 volts PWM charge controller to regulate input into the battery bank. Let's look at another example. Imagine you're designing a system for a small ICT hub with 50 laptops, 2 ceiling fans, and 4 security lights, using 4 12-volt 200 amp-hour gel batteries. How would you approach it? Take a moment and think. The key steps are the same: total load calculation, inverter selection, then sizing batteries and panels. First, we estimate the total power of the appliances given. Laptop is 50 times 60 watts, which gives 3000 watts. Ceiling fan is 2 times 100 watts, which is equal to 200 watts. Security lights is 4 times 18 watts, which gives 72 watts. This gives a total power of 3274 watts. To size the inverter, we will consider the total power of 3274 watts and select an inverter model with specification 5 kVA, 4000 watts, 24 volts. For the battery sizing, we already have 4 pieces of 12-volt 200 amp-hour batteries available. Take 2 batteries and connect them in series. This is done by linking the positive terminal of the first battery to the negative terminal of the second battery. This pair will now act as a single 24-volt battery with a capacity of 200 amp-hour. Repeat this process with the remaining 2 batteries to create a second, identical 24-volt 200 amp-hour pair. Next, you will connect the 2 pairs you created in parallel. This is done by linking the positive terminals of both pairs together and the negative terminals of both pair together. This connection will keep the voltage at 24 volts but will double the total capacity, making it 400 amp-hour. For the PV array sizing, using the standard stated in example 1, 10 to 15% of the amp-hour of the battery bank is 40 to 60 amp. Let's consider a solar panel module with specifications: 500 watts, maximum operating current of 10.55 amps. Maximum operating voltage of 9.43 volts. An open circuit voltage of 56.48 volts. We will have 6 panels connected in parallel to give a total output current of 60 amps. When sizing the charge controller, we take into consideration the charge current of the lead-acid battery, which is calculated as 60 amps. Therefore, considering the charge current and voltage of the battery and inverter, we will select a 60 amp, 24 volt MPPT solar charge controller. Remember, a good installer always adds some margin because appliances often consume more power than stated on their labels. To sum up, system design involves load calculation, inverter selection, and matching the right batteries and panels. With practice, this becomes second nature.